Hello and welcome back to another lecture on this NPTEL course on advanced plasticity of solid continua. So, we have been discussing about rate dependent plasticity. If you recall, it is essentially the question of the loading rate influencing the final solution, not just the initial and end point of the load. Right. So, the rate at which you go from the initial to the end point, that also matters in rate dependent plasticity. Now, we have also been talking about the convex analytic route to plasticity, right, which the usual textbooks do not really much dwell on. The reason for this, as I have been mentioning again and again, is that we have a variational formulation possible through convex analysis. That means an energy minimization that you do in the standard finite element for elasticity, right, can be done here too. So, therefore, when we transition from finite element analysis of elastic problems to finite element analysis of plasticity through this convex analysis based route, then we do not have to see something drastically different, right. So, this is why we have been discussing about the time discretized. So, this is what actually we will be talking of. So, time discretized variational problem which we will be setting up to solve the plasticity problem. Okay. So, with this in mind, let us first do something simpler. That means you may be knowing, some of you at least may be knowing about this, but I thought that in order to transit smoothly from elasticity to plasticity, you should know where exactly this transition occurs and what is this overarching variational principle that governs both elasticity and plasticity problems. Okay. So, let us now discuss how the standard elasticity problem under small deformation, right, can be solved by the finite element method. All right. So, this is just a recap. It is understood that you know about it, but I am not assuming that you have to recall everything. That is why I am trying to have a recapitulation of the essence of this method. So, but let us consider an elasticity problem, small deformation, but not linear. Okay. A linear problem is a simpler case which always can be adapted. But let us consider a nonlinear elasticity problem. By that we mean that the strain is small, but the stress strain relation is nonlinear. All right. So, therefore, stress is not a linear function of strain, even though the strain is the small strain here. All right. So, the advantage of small deformation, if you would recall from our discussion quite some time back, is that there is only one configuration to bother about. Okay. And please be informed once more, because this is very essential to this, that the stress strain relation is nonlinear. Linear relation is a special case of what I am going to describe. All right. So, the variational problem that we solve typically to solve for the unknown displacement u is the minimization of a total energy. Okay. Call it by pi u. Pi is a function of the displacement field u. This expansion for this pi u, the expression, detailed expression for this pi u, it consists of three parts. One, it consists of the strain energy functional for, in the context of a dissipative problem, for example, thermoelasticity, we do not use the word strain energy, we use the word free energy. All right. But otherwise, assuming there is no thermal effects here, psi is basically the strain energy functional, which basically is essentially a function only of the small strain, which in turn can be expressed in terms of the displacement u. All right. But There are also two other terms, one related to the body force. Okay. So, the body force acting on the displacement producing some work, this is the external work. Another piece of external work, another contribution to the external work is offered by the traction which is applied to the Neumann boundary. There is a slight mistake here, let us call omega n as the normal boundary, okay, Neumann boundary, omega n, okay, and let us say omega d is the Dirichlet boundary. So, omega union, sorry, del omega n is the Neumann boundary and del omega d is the Dirichlet boundary. The union of these two recovers the total boundary del omega. Okay, that means there should be no gap between the Dirichlet and Neumann boundaries, right. So, actually no boundary should be left without a specification of the boundary conditions, that is not allowed. Anyway, so this is the details of how you construct pi, that is the total potential energy, right. Now, so you remember that even dynamic problems come under this purview. In the dynamic case, this the body force B will consist of the usual body force plus also the inertial force, all right. So, this is the generalized body force that we are talking of. So, static and dynamic problems are both incorporated within this setup. Let us now talk of the stationarity condition, right, because we need to minimize pi with respect to u, right, but u is a field, it is not just a vector, it is a vector valued function, right, function of x. So, we typically talk of the variation of pi, I mean in the same language as we use in the principle of virtual work and things like that. Okay, so, we basically take a variation of pi by taking a variation of the function u about the function which actually minimizes pi. We do not know that function which minimizes pi, but if u is that function which we have to find, then we need to probe the neighborhood of u, right. So, we need to change u to another function locally by not changing too much, just probe the neighborhood to see that indeed this del pi, which is the variation of pi because of the variation of u, goes to 0. This is basically the same thing as taking the derivative of a function and setting it to 0 to find its minimum or maximum, right. So, it is basically a generalization of that same principle. So, if you use this fact, that is if you use this variation on the expression for pi, right, you are basically changing only u, right, in a virtual manner, which leaves your sigma, the stress, all the force like quantities like sigma, the stress, B, the generalized body force, and script T, the traction applied to the Neumann part of the boundary. All of these are left untouched, that means they are not modified, they are not varied. What is varied is only those parts which are directly functions of u, for example epsilon, right. So, remember that sigma is basically a conjugate quantity. You can do the same thing by actually finding something called pi star, the conjugate to pi in terms of sigmas and the force like quantities and minimizing that, but we are not doing that. We are actually taking epsilon to be the or u to be the unknown. So, delta epsilon means the variation of the epsilon, which is basically the strain due to the variation in u. Okay. Think of this as a virtual variation, it leaves all the forces untouched or unchanged. Now, we already know from the Coleman-Knoll principle the closure condition, which is that sigma is basically given in elasticity as equal to del psi by del epsilon, right, the constitutive closure by Coleman-Knoll, you need to recall that. Now, so what basically this statement is, basically this statement is nothing but a statement of the principle of virtual work, around the equilibrium position, which is u, if you modify the equilibrium position by a virtual displacement field, then the corresponding work will also satisfy the principle that the external work is equal to the internal work. All right. So, this is the principle of virtual work, which we have probably discussed earlier. Okay. So, this is basically now being applied to the elasticity, nonlinear elasticity problem. The FEM, the finite element method based discretization, is very standard, right. To be sure, there are many other complicated forms of discretization in finite elements, but we are not bothered about that. Take the simplest form of discretization, which is the displacement field ux is approximately, okay, is equal to summation over I nix ui. Ui's are the nodal unknowns, the nodal values of ux at the nodes, xi's are the nodes, right. Nix is are the shape functions, nix is the ith shape function, that means the shape function corresponding to node I. Let us call the collection of all the nodal variables, displacement variables by the capital U. Okay, it is a vector now, it is no more a function like small u is a function of x, right. So, these are the discretized displacement degrees of freedom in the finite element method, right. Now comes another change, because we really do not work in finite element implementation of elasticity with strain as a tensor, because then the strain displacement relationship becomes more complicated to write in a computer. So, therefore, since strain epsilon is basically symmetric, so therefore, it is a 3 by 3 matrix, a symmetric 3 by 3 matrix will have 6 unknowns, right. So, we write this strain and the stress as 6 dimensional vectors, right, because stress is also symmetric like strain. So, let us call them by epsilon hat and sigma hat, this vector representation of strain and stress respectively. Remember that this is just a computer based implementation artifact. Stress and strain are never vectors. Okay. So, now the corresponding the elasticity tensor, which is basically 4th order, could be written as a matrix then, right. So, because sigma hat is a vector, epsilon hat is a vector, so therefore, C will be a matrix. So, you take the original elasticity tensor and represent it properly, okay, through a matrix C, so that it reproduces the known stress strain relationship. Okay. So, C is a matrix, it is basically a 6 by 6 matrix. So, therefore, but C basically in this particular case, because I already said that sigma and epsilon are non-linearly related, right. This is a non-linear elasticity problem. So, it is possible in this case that C will still be a function of displacement, or after discretization C will be a function of the discretized displacement vector, which is all put into the this capital U, the displacement discretized vector DOFs. So, the strain displacement relationship is very standard, because strain is a linear function of the displacement for small strain, right. It is the symmetric part of the gradient of U, correct. So, we can therefore in the vector matrix form, we can write the strain displacement relationship epsilon hat to be equal to B times U. B is called the strain displacement matrix, you may be knowing about it, right. So, it is related to, you find B by taking the appropriate derivatives of the shape functions Ni, because from here you can find out the strain epsilon is the symmetric gradient of U, right. So, that symmetric gradient, if you apply to this finite element approximant, then you can understand that what we will be having is the derivatives of Ni entering in constructing this strain displacement matrix B, right. So, epsilon hat is equal to Bu. I am assuming that you know what is a strain displacement matrix B and how to construct it. If you are not very comfortable, you can actually go back at this stage to a basic finite element text or a suitable NPTEL lecture on finite element method and refresh your memory on how to construct B. Okay? Now going further, we basically from this relationship we actually take a variation and virtual variation, and we write delta epsilon hat is equal to B times delta U, right? Remember that B does not get affected by this variation because B is not a function of U. Okay, so now let us talk about the discrete variational approach, continue talking about it. So you remember the expression for delta pi, correct? Delta pi here, this delta pi, here is this delta pi equal to 0, right? So one of the terms that we have interest in delta pi, the first term is integral over omega sigma inner product, the virtual variation of strain integrated over the domain. Okay. So here let us put in the strain displacement relation to further simplify this quantity delta epsilon, which gives you B delta U. Okay. But now in terms of vectors it is a dot product, it is basically an inner product still, but a dot product between sigma hat and B delta U. Remember that B delta U is a vector. Alright, but now this integration is over omega, that is over the coordinates. B is a function of the coordinates, right, but not capital U, because capital U is defined only at the nodal points, the set of displacement degrees of freedom DOFs. So therefore that comes out of the integral, and you take the dot product through the transposition of the vector delta U, right, and you have this integral over omega B transpose sigma hat sitting as the integrand. Okay, so we can therefore think of this quantity as the internal force F internal, which acting on the discrete displacement degrees of freedom in the virtual form delta U is producing the virtual work. You see that point? Okay, so F int is the corresponding internal force. Similarly, I can do the same exercise for the other terms, which are essentially the external forcing based work, right. Virtually we have to do that. That means, you know, we basically get the correspondingly the F external, because you know there is, even though see we are actually virtually changing U to delta U, but this external work, if you just take a look, so let us take a look at this, you know, the expressions. So delta U comes here, right, exactly in the same manner. If you replace this delta U by this delta capital U appropriately upon discretization, right, and then you actually finally come to an expression for F external forces, which basically produces the external work by this delta U transpose, you know, F external gives you the external, oh sorry, F external is on the top. Okay, that gives you the external work, virtual work, right. So the external expression for the external force is just here. All right. Remember that the external force does not depend on U, but since it is a nonlinear problem, this internal force does depend on, I mean even for a linear problem it will depend on U, but since it is a nonlinear problem, this sigma hat is a nonlinear function of capital U. Please remember that. Okay. So here B hat and T hat are the discretized forms of the body force and traction. So therefore the residual equation, right, takes the form, this is called the residual, because now you see you take delta. So basically what do you have? You have F external delta U transpose, right, if you take it common, minus F internal, that is basically equal to 0, correct. So delta U is entirely arbitrary. This delta U is basically a virtual variation, so let us call it that way. Okay. So therefore, for any arbitrary such a thing, if this 0 has to be realized on the right hand side, the only way of ensuring that is that f external must be equal to f internal. This is the similar to the localization principle that we have been talking about. So therefore, you understand that this gives us the difference between f internal and f external gives us what is called the residual, which is now a function of u. Remember that only f internal is a function of u. Okay, this is the nonlinear algebraic system for u that we must solve, and observe that the virtual variation delta u has vanished, because we have taken it out and thrown it upon this, this argument from which we got f external is equal to f internal. Right. So, a nonlinear algebraic equation is typically solved by the Newton-Raphson method, right. So, we need to recap that also a little bit. So, Newton-Raphson method for the solution of a nonlinear algebraic equation is an iterative principle, right, based on Taylor's expansion. Now, so you must recall what is the Newton-Raphson method. We may not be having the time to go through it in great detail, but let us proceed with the understanding that Newton-Raphson method is iterative in principle. So let u be the last available solution. That is how we do iterative solutions of nonlinear algebraic equations. We assume some last available solution. To start with, we have to have a guess, right, and then let delta u be this delta u. Now with a triangle delta u be the update, so that we will be having the final solution at the kth iterate as uk plus 1, that is the solution at the end of the kth iterate, is the solution at the beginning of the kth iterate plus this delta u, right. So what is the corresponding equation that you need to solve? It is a linear algebraic equation, because you need to linearize this f internal u properly, okay, and you get k delta u is equal to minus ru, this equation. So remember that minus ru is a known function of u, because it is the last available u that we are talking of. Delta u is the unknown, k is basically the corresponding matrix which should be invertible, right, that is the thing. This k is called the consistent stiffness matrix. What is the expression for k? Because we are minimizing the residual r as a function of u. So clearly k is basically del r by del u. So what is basically that we have? Del r, so k delta u is equal to minus ru, correct? So what does it mean? It essentially means that delta r by delta u, okay, this delta u plus ru equal to 0. This is an approximation of ru, right, about u. You understand? This is, so if your correct solution is not yet known, right, you have to find it. So this is an approximation of ru, but this u and this u are not the same. This u is the last available u. So you do not mistake it, okay. So it is an approximation of ru, right, and r is already a derivative with respect to the with respect to pi, right, with respect to the strain energy psi. Do you remember? So this is essentially a second order derivative, all right, that has to be understood. So now let us derive an explicit expression for this k, right. So k is basically delta u of r. R has an expression which is given earlier by integral of over omega b transpose sigma hat d omega. We derived it, right. The other part of r does not really depend on u, right. The only part which depends on this u is this, okay, that is the f internal, okay. So so therefore b, the strain displacement relationship matrix, is independent of u. So basically we can write K is so you can take this delta delta u inside and differentiate sigma with respect to u, in this case the vector representation of sigma which is there in sigma hat, and we have this expression for the tangent stiffness matrix K. All right. Now let us use a chain rule on sigma hat. Okay. So chain rule on sigma hat means I know my capital U dependence of epsilon hat. I do not directly work with the U dependence of sigma hat. I would rather work with the epsilon dependence of sigma hat, right. So there is a hat missing here. So this is basically delta sigma hat by delta U is this factor delta sigma hat by delta epsilon hat times delta epsilon hat by delta U. So this now delta epsilon hat by delta U is what? It is nothing but, see, basically strain displacement relationship is given in matrix form, matrix vector form in finite element by epsilon hat equal to B times U. So delta epsilon hat by delta U is just B, the strain displacement matrix, which is this factor. Okay. So we now also recall that delta sigma hat by delta epsilon hat is given by this matrix C, this C which was found from the elasticity tensor script C, right, as a matrix. So therefore we can say that this C, which is a function of capital U now because of the nonlinearity, is essentially delta sigma hat by delta epsilon hat, right. And we can write this overall delta sigma hat by delta U as C times B, both are matrices, right, and delta sigma hat by delta U now is a matrix because sigma hat is a vector, capital U is also a vector. So delta sigma hat by delta U, the gradient of a vector with respect to another vector is a matrix, right. So this is basically the scenario. Okay. So C, remember that it is delta sigma hat by delta epsilon hat, but sigma hat is delta psi by delta epsilon hat, right. So therefore this is the Hessian of psi, this C is basically the Hessian of psi. So this is what is important, this Hessian structure of the material information as captured in this strain versus stress relationship is captured here through C. Okay. So this is called, that is why called the material tangent stiffness, this C, okay, unlike K which is called the tangent stiffness or the constitutive tangent, all right. So this is the continuing with our discrete variational approach, we therefore have the final expression for the tangent stiffness. If you recall, the tangent stiffness is basically B transpose delta sigma hat by delta U, but we have already found delta sigma hat by delta U is equal to C times B. C is the matrix form of the elasticity tensor and this appropriately linearized, and B is the strain displacement relationship. So basically we have this standard relation which is true even for the linear case, except that C is for the linear case not a function of U, all right. So we have this expression for K, integral B transpose C B d omega, all right. So this basically in finite element we do this K calculation of K, this tangent stiffness element wise. That means we define the element based tangent stiffness as K E, integrate to get this K E over the element omega E, correct, and then assemble. Similarly we get the right hand side, that is basically, so we need to solve for this equation, right. You remember that K delta U is equal to R U minus R U, right. So we get the right hand side appropriately through the the vector forms, discretized forms of the B and the T, that is the traction and the body force. Anyway, so basically so we also find the internal F int representation element wise through this relationship, okay. Now let us actually go through the whole thing step by step, but we have now set it up, Okay, so what we have so far done, I will actually continue with this talk further when we actually describe the iterative algorithm. But so far let us understand one thing. What we have tried to do is basically linearize the problem. The first requirement is also a form of linearization, which is delta pi equal to 0. That requires the derivative. Any derivative you take, you are essentially linearizing. Okay? But that does not fully linearize the problem. Delta pi equal to 0 is rather thought of as the condition for stationarity to find the equilibrium solution. That is a condition for optimization. On the other hand, delta pi gives you the stress, the requirement that external force is equal to the internal force, and it is the linearization of the internal force which brings in this tangent stiffness information k, or the equivalent, the material tangent information c, okay, through the Hessian del square psi by del epsilon square. Okay, so this is what we must understand, and this has to be solved within an iterative framework. So we will come to this iterative framework in the next talk. So this was essentially just a warming up towards actually stating the different steps which basically we take in the finite element analysis of nonlinear elasticity, through which the transition to nonlinear problems in plasticity, that is plasticity is itself a nonlinear problem, through the convex analysis becomes pretty smooth. Okay, so we will come to this in the next lecture. So thank you for your attention, and we will come back soon. Thank you.